Okay, I think we are live. I
We
have no
are.
idea if anybody's watching.
Yeah, it says
Okay,
says live in the
so,
upper.
all right, so hello. We are doing a quick little hangout on air to talk about the Big Bang. There's been a lot of talk about the Big Bang in the news lately. There have been papers coming out saying things like the Big Bang didn't happen and stuff like that. And so we're just gonna sort of talk about what it means, what the Big Bang means, how we know it happened, different things that people mean when they say Big Bang, and what we've learned about the Big Bang, and what we are learning about the early universe, and sort of all that jazz. So we have a great lineup today. Um, I've gathered some of my favorite Twitter people to talk about this with me. So I'm Katie Mack. I am a theoretical cosmologist, and I study things like the early universe and dark matter and stuff like that. We also have Amanda Yoho, who is an expert on the cosmic microwave background, and she's going to tell us a little bit about how we learn about the Big Bang from the afterglow of the Big Bang, the first light in the universe. Then we have Matthew Francis,
Hello.
who's going to talk to us a little bit about general relativity, because that's his deal. And then we have Robert McNeese, who is a particle physicist, and he's going to talk to us about how we can learn about the Big Bang in the laboratory. So, okay. So I'm just going to start the discussion with what does the Big Bang mean? What is a Big Bang? What do we mean when we say that? So first of all, from a cosmologist point of view, the Big Bang has a very specific meaning. Maybe Amanda, you can tell us a little bit about what we mean when we talk about the Big Bang as cosmologists.
Yeah, so it's a little bit ambiguous, I think, when we talk about this kind of thing because oftentimes I think people hear the Big Bang and they think starts from a singularity or from a single point. But oftentimes what we mean when we say Big Bang is the hot Big Bang. So the fact that we know everything was in contact with each other in this really hot, dense soup of stuff that expanded very rapidly and now has formed into the universe that we see today. So we have a lot of evidence in favor of the hot Big Bang, and I think that that's one of the key points that was missing from some of the latest articles that mentioned things about disproving the Big Bang and stuff like that.
Yeah. So the hot Big Bang is I guess the way that as a cosmologist we would talk about that sort of early state, but when we just say the Big Bang theory, that's what that is, right? Like the the
Right.
whole singularity thing is like a separate aspect.
Right, exactly.
So what is okay? So that's the hot Big Bang, and that's the thing that I think that's the most misunderstood. But then there's also the singularity itself. Now that's this idea that the universe started in a single point, and that idea has been around for a long time. I think originally due to people like Hawking, and that's something that makes sense theoretically, but it's not quite as generic as just the universe was hot and dense in the past. And now, Matthew, can you tell us a little bit more about the singularity and what that means?
Yeah, well, I mean, if you think about the universe that we see today is expanding, meaning that um, what we're seeing is galaxies seem to be getting farther apart as time goes on. That means that farther back in time, they were closer together, packed more densely, and before there were galaxies, matter was all crammed together even more tightly. And so if you keep running that clock back farther and farther, eventually everything you see, everything, must have existed at one single point. Now, that's according to if we are just naively looking at what the equations tell us and what the observations tell us. But we don't have direct observation of that. We can't go back that far with our observations. And in fact, we can't even go back that far really with our theories, because at some points our theories break down, and I think Robert's going to talk a bit about that. But so the singularity is this idea that inevitably there's going to be all this stuff packed together in a single point. It is an inevitability. I can speak English, I swear. At the first instant is a generic prediction of general relativity, but it isn't necessarily the it isn't necessarily so. Nobody really, I shouldn't say nobody, but almost nobody believes that general relativity is a full description of what happens at the very earliest moments in the universe, simply because general relativity does not describe quantum stuff. It doesn't describe the interactions between particles that we understand from quantum physics. So what happens, we don't know yet. And that might even include some crazy ideas like, maybe there wasn't a singularity at the beginning. That does not mean there was no Big Bang as we understand it, because like Amanda was saying, all the Big Bang means is that at one point in the past, all this stuff was packed together that we see. And so the singularity, we really I almost always avoid talking about the singularity for that very reason, because it's something that we do not currently have access to. We don't understand what's happening there. So but that does not mean that the Big Bang is in question in any way, shape, or form. Even if that singularity didn't happen, even if the Big Bang as we understand it was not the beginning of all time, there's a very good chance that it wasn't. That doesn't mean the Big Bang didn't happen, because the Big Bang is a very concrete set of descriptions of our universe that we inhabit as we observe.
Okay, so you're saying that the singularity itself is inevitable if general relativity can be dialed all the way back, but we already know that general relativity breaks down with quantum mechanics, and we know that when you get to those really dense states, quantum mechanics becomes really, really important, and you have these strong gravitational effects, and it's something weird is happening, right?
That's right. And honestly, I think probably inflation is something we don't want to get into too much tonight, but there's the idea, and maybe again Robert may pick up on this, but the notion that the universe expanded one theory is that the universe expanded very rapidly in a split instant after the Big Bang, and due to quantum effects. And so basically that makes it even harder for us to see what happened before inflation, because inflation would kind of wipe out a lot of the information of what occurred before that. So again, the existence or non-existence of the singularity has nothing to do with the existence of the Big Bang. Which is just a statement basically about expansion and how hot things used to be.
Okay. So, Robert, maybe you can talk to us a little bit about what we think was different about the physics in the early universe. So we know that we had this hot dense state, and we know that the laws of physics change when you get to these really high densities, really high energies, and we're simulating some of that in the laboratory, right, with gliders and stuff. Maybe you could talk to us a little bit about that.
Yeah, well, so like Matthew was saying, a lot of the conclusions that people draw about the Big Bang and a singularity come from taking general relativity, which is a completely classical theory, and running it backwards. And you do things to try to accommodate the fact that that stuff is quantum mechanical. You do what's called semi-classical gravity, where you're mixing classical general relativity with quantum mechanical everything else, but ultimately you don't have a quantum mechanical theory of gravity. And so the further back you go, the more and more extreme conditions are, your understanding of how things work starts to break down. So when people ask this question, well, if we run things backwards, was there a singularity? There are a lot of different ways you can try to answer it in the context of what's going on at higher energies. And some people try to avoid the problem altogether. They try to find ways where, even almost in the context of classical GR and quantum field theory, you can kind of circumvent the need for a singularity. But other people say, well, let's take this serious. When we talk about singularities in other places in nature, right, the other place we talk about is black holes, right? So we imagine that there's something singular going on behind a black hole, but we never say, well, that's got to be the whole thing. We say, all right, fine. This is a signal that physics is changing. It should be operating. There should be different rules, different laws that explain what's going on under such extreme conditions. And so you turn to quantum gravity. You say, well, maybe we have to quantize gravity, and then that would give us some kind of complete description of what's going on, where we could address questions like singularity. So when you run the clock back and try to ask these questions about a Big Bang singularity, I think you run into the same situation. So people take different approaches to quantum gravity and try to use them to, I don't know, to kind of throw out explanations for either how to address a singularity or how to avoid one. You know, they take these nascent ideas we have about quantum gravity based on frameworks like string theory or loop quantum gravity, or even older work from the 70s, Euclidean quantum gravity, the stuff that Stephen Hawking did, and say, well, okay, if we take these theories seriously, what would they say about those earliest moments? And there's a range of answers. I mean, there's a range of ideas that people throw out there. There are all kinds of proposals for how you either avoid singularities entirely or replace them with something else. But in all those cases, the scales, the energies we're talking about are really, really far beyond, you guys all know, what we see in colliders, right? Even the LHC now is gearing up for this run where kind of peak center of momentum frame energy is, on the order of like 14 TeV. But we're talking about phenomena that are conceivably more like, 10 to the 16, 10 to the 18 GeV. So many, many orders of magnitude past what we expect to see in colliders.
So what do we learn from colliders? How does that tell us about maybe not the singularity, but the Big Bang itself?
Well, a lot of what, if we go back and we follow this hot Big Bang, and we kind of go back as far as we can to very hot, dense conditions, a lot of what happened from a pretty small fraction of a second. I don't want to say after, because we're trying to get away from this idea of saying things started at a particular time, right? But we push it back as far as we can, and we push it back to many, many thousands of millions of degrees Kelvin and very, very high energies. And we understand pretty well what went on. When we try to push it back too far, we have to kind of throw up our hands and say, well, I don't know what to do with the singularity. But as far as things being in thermal equilibrium, and then the universe cools off a little bit, and all of a sudden protons and neutrons can, begin to form bound states, and that is pretty well understood within the framework, the framework that we have. But then there are these other questions that aren't quite resolved yet, like, well, at some point we established this matter-antimatter asymmetry, and we don't quite understand why that happened. This whole question of, well, if we have something like inflation, how does something like that fit within the standard model? So, one of the discoveries that's happened in the last few years in particle physics is, of course, the Higgs boson. And one reason that's compelling from the point of view of cosmology in the early universe and the Big Bang isn't that that's an example of a scalar field, and a lot of models of inflation, a lot of these ideas people have about the very, very early universe rely on these entities, scalar fields, that up until the Higgs boson came along, we didn't have any real examples of fundamental scalar fields. We didn't know that there really were such things. So now we do.
And that's an example of something that might be more important in the early universe than today, in terms of how the sort of physical interactions are going on.
Exactly.
So let me move the conversation a little bit toward what we see in the sky that tells us about the Big Bang. So, Amanda, you've been working on the cosmomicrowave background. From my perspective, the cosmomicrowave background is the best evidence that we have that the Big Bang happened, and basically amounts, I would say, to proof that the Big Bang happens. I mean, it's hard to prove something in science, but we can see it. I mean, we have pictures. Can you tell us a little bit about that?
Yeah, so this was one of the most interesting titles I think that came up recently with these articles was something about are we in a Pixar it didn't happen situation with the Big Bang? And I thought that
Right.
was funny because we have a picture of the Big Bang. It's the cosmic microwave background.
Yeah.
So yeah, the reason that that is direct evidence of the Big Bang is because, as we said, we know that stuff started really close, densely packed together, really hot, dense sort of soup. And anything that's in that kind of contact with each other that has some kind of energy associated with it, what's called a black body spectrum. So any kind of thermally connected material will emit this particular light in a characteristic way in
So
what's called the black body spectrum.
This is just stuff glowing because it's hot, right?
Yeah,
if you
exactly.
Put a poker in a fire. Yeah. Okay.
Yeah, exactly. So it emits light in a very particular way, which is characterized by what we call the black body spectrum. So we look out into the sky at the cosmic microwave background, and we see exactly a black body spectrum of 2.73 Kelvin. And it's so exactly measured that the error bars on the points are smaller than the thickness of the line that's usually used to plot the spectrum of emission that we see in the CMB. It's crazy. So I think there was a plot that I put on Twitter a couple of weeks ago where they had blown the error bars up to be 400 sigma error bars, and it was still an amazing fit. So yeah, we know that at some time in the past, which the CMB is coming to us from a little less than 400,000 years after the hot Big Bang, that it was a densely packed hot thermal ball of stuff, and we've measured that. Now, it's 23 years ago, I guess. It was 1992 that Kobe first measured this, so this isn't a recent development. This is something that we've known about for a while now.
Can I just, I'm just going to screen share. I found that picture that you were talking about. This is the error bars blown up only 200 times. But you can still see, like,
yeah.
You basically can't.
Yeah.
I mean, that's about the best kind of fit you're ever going to have in any kind of science, and
right.
And that's just
and the
it's
line
something
that's
glowing because it's hot.
Fit here. Yeah, exactly. And the line that's fit here is something that we predicted with equations before the data came. Well, this is the line that just should look like for something with a particular temperature, and it turns out that the CMB exactly matched that prediction.
Yeah. So that, I mean, that basically tells us that the whole universe was glowing because it's hot, right? Because we see the CMB in every direction.
Right. Exactly. Exactly. So that's that kind of goes back into, I don't know how much we want to talk about.
Your sound is breaking up a little bit.
Or anything like that. But any direction that we uniform 2.73 Kelvin black body, but then we have these teeny tiny fluctuations on top of that, which for my money is where we get the best kind of science out of the CMB. But this was the big first kind of success of CMB observations.
So yeah, so I guess just in case something I always feel like I need to make clear with the CMB. We see this radiation coming from every direction, and the reason for that is that as you look farther away, you're looking back into the past, and every direction we look, we're looking back into the past for that point. And what we can see is that every part of the universe was at some point glowing with this heat, and the question of why everything was the same temperature across the whole universe, that gets into inflation, and that's kind of another question. But we do know that there was this hot thermal state, and that seems to have been just what the universe was like at early times, and that's where the hot Big Bang idea comes from. Now these little fluctuations that you can see in the picture of the cosmic microwave background, that tells us all about how structure formed in the universe, how we get galaxies and stars and things like that. but just the existence of the CMB. Now, do you know that this was predicted before it was found, right? There were a couple of theorists in Princeton, I think, that said something about this.
Yeah, it's I should remember this history, but it was one of those things where I think maybe 2 or 3 different groups had sort of said, oh, well, we predict that there's going to be this level of uniform radiation that measures. A couple of researchers from a Russian university, and then there were a couple of guys at Princeton. I think 2 at Princeton are the most well known, and every time I talk about it, people make sure to remind me that there were, in fact, other groups that had also predicted this uniform background temperature. But yeah, it was these 2 guys at Princeton also were people at Bell Labs, so Penzias and Wilson, 2 people. I think they were trying to do some kind of communication balloon experiments or something like that. They were bouncing microwave signals off of these balloons, and they had to get really, really precise measurements. So they were picking up this background noise that they hadn't accounted for otherwise, couldn't figure out what it was, and then eventually someone who knew these guys at Princeton who were doing these kind of writing papers predicting the CMB background temperature said, oh, no, actually you're seeing what we talked about here. This is relic from the Big Bang in the universe. Really led to a Nobel Prize for those 2.
They spent a couple days scrubbing their radio. So they had the horn antenna, and they spent a couple days scrubbing it out because they thought it was noise from debris from pigeons that had been nesting actually in the antenna.
Yeah, there's actually...
Scrubbed it out, and it was still there.
Yeah, there's a bit of a sad story about what happened to those pigeons, but yeah, it turned out it wasn't pigeon poo. It was the afterglow of the Big Bang.
Oh,
and
no.
that was sorry.
Yeah, I mean we should all acknowledge their sacrifice.
Yeah. So the one thing I think is cool about the cosmicrowave background is that was predicted just from looking at the expansion of the universe, basically. So the people who predicted that the universe should have been, this hot glowing thing, and we should be able to pick up the glow from the early universe, they got that from just saying, look, the galaxies are all moving away from us, the universe is expanding, let's dial that back, and what do we get from that? And they were able to predict, reasonably accurately the temperature of the early universe, what we would be able to see. So that was kind of a cool inference.
In a way, it's kind of the best piece of information, or the kind of best piece of evidence for the cosmological principle, right? Because it's the one thing that we look in every direction, and you see homogeneity and isotropy to like 1 part in 10 to the 5th, right? So it's really kind of a phenomenal piece of evidence that things are basically the same everywhere and look the same in every direction. And that's that kind of implicit assumption that underlies all these things that we talk about. Right, that on large scales the universe is basically the same everywhere and looks the same in all directions. And we talk about we run the clock back and we expect this to happen. That's kind of underlying all these things. So it's good to have that kind of strong evidence.
And that kind of the universe is the same everywhere idea is part of why we can do things like create collisions in the laboratory and get to those same energies that we expected to see sometime during that hot Big Bang phase. And from the result of those experiments, assume that we've learned something about the early universe, because we know that the laws of physics are the same everywhere, as far as we can tell. And so if we can create the same conditions that occurred during the hot Big Bang, then we expect that the physics that we see in that collider is the same as the physics that occurred during the early universe, and so we can actually tell something about how the universe was evolving, what happened in those first few moments, by just creating a collision at the same energy. Now, one of the things that maybe is a little bit too esoteric to get into much is the way that physics changes when you get to higher energies is really interesting, I think. So there's this concept that you have these different forces of nature. You have the electromagnetic force, you have the weak nuclear force, the strong force, all of that. And the strengths of those forces are different when we measure them today, but they change as you go to higher energies. And so there's this concept that in the early universe, those forces may have all been aspects of the same interaction, the same force. Robert, can you say just a little bit about that, just as a sort of aside?
Right. So I guess even since the 19th century, probably with the work of people like Maxwell, there's always been this theme of taking interactions, rules that govern the way that matter behaves, and fitting them together into kind of smaller, simpler frameworks. Right? We used to think of electricity or kind of electric forces and magnetism as different things, and then we realized that no, they're aspects of the same thing. And if you have relativity and electric forces, you have to have magnetic forces, and so we think of them as electromagnetism now. And then in the 50s and 60s, particle physicists realized that what we think of as electromagnetism and what we think of as the weak nuclear force, kind of primarily responsible for nuclear decays, were also aspects of kind of a single phenomenon. And then we have this third force, the strong nuclear force. It's described by a theory called quantum chromodynamics. And as you turn up the energy, the strengths of the interactions change. This is a very important feature of quantum field theory, which is the framework we use for doing particle physics. So as you turn up the energy, all this kind of strengths of all the interactions, their significance, how important they are, all kind of head towards the same point. They all kind of begin to converge. And it looks like somewhere, still many orders of magnitude above what we can hit. Right now in accelerators, we're probing things that have to do with electroweak unification. Right? So we're studying the Higgs and related particles. But if we kept going higher and higher and higher, these strengths of the interactions begin to converge, and you expect that they're all going to kind of fit into a single framework. But even when you get there, when you get to the point where the strong force and electroweak begin to be of similar importance, gravity is still kind of a long ways off. You still don't know what to do with gravity. It's still several orders of magnitude away. And I guess the expectation is that somewhere around, so like we said before, at the LHC right now, we're expecting something like 13, 14 TeV of energy. So that's 13 or 14 trillion electron volts. And the Planck scale, the scale where we expect to have to worry about this with gravity, is more like 10 to the 18 GeV. So 10 to the 15 TeV, right? 1,000 million orders times larger than the energies we're talking about at the LHC. So the further you go back, in the hot Big Bang scenario, the denser and more energetic things become, and you're playing by different rules. It's not the rules that we use to describe, say, what's going on in most astrophysical phenomenon, say, or even in the colliders. It's we even have to kind of go beyond that, and presumably at some scale these forces are unified, and understanding that would kind of be an important part of understanding, pushing back how far we can go in the hot Big Bang.
So we should probably wrap up in a moment, but just wanted to say one more thing about that. So when we talk about unifying the sort of subatomic forces, the electromagnetism, weak force, strong force, that falls under what we call grand unification, grand unified theories, or call them GUTS, I guess, in particle physics. And there's a step beyond that, which is theories of everything, and that's where, I mean, when we as sorry, yeah,
toes.
Yeah.
This is like guts. You have guts and toes.
Yeah. So as physicists, when we talk about theories of everything, that's really what we're trying to get at, is unifying all the forces, not just the subatomic forces, but also gravity, and getting that in there too. So just in the last minute or two, maybe Matthew, you can tell us just a little bit of about what we're trying to do with theories of everything and where we're at with that.
Well, that's a good question. In a sense, we haven't gotten very far with theories of everything. We know where the problems are. We've identified them fairly well where where the problems are with trying to bring gravity into the fold in a way. But there's even bringing the strong force in with the electromagnetic and weak force. We still have some missing pieces with that. And actually, that's a place where the LHC is going to be giving us a lot of help on, presumably. But bringing gravity in is really a problem because gravity doesn't play well with the other forces. It doesn't look like the other forces. It doesn't act like them. So there have been a number of approaches over the years. Probably the most popular one is still string theory, which is a way of treating particles as not as fundamental themselves, but as vibrations on strings that exist in dimensions beyond the one we can observe, with the extra dimensions all being curled up very tightly. That's probably the most popular approach to unifying the forces that exists right now. There are other ideas out there as well. But the main thing is that we do know where there are certain where we have certain lack of knowledge. We know as we get towards the Big Bang that eventually the force of gravity is going to become, which is by far the weakest force in the universe, even though it's obviously the one that we feel the most strongly in our bodies as we walk around and complain about our backs, or maybe that's just me. Gravity is by far the weakest force in the universe, but as we run toward the Big Bang, it will eventually become the same strength as all the other forces. At least that's, if everything we know is consistent, it will be that way. And so what people have been doing is looking at exactly how that might be. Are there clues we have in the structure of the mathematics, but also are there clues in crazy places like black holes where gravity becomes very intense? Are there clues where gravity is very weak, like dark energy? There's all sorts of ideas, and we may not understand the answers, but we're getting better at asking the questions, and maybe that's what physics is about in the end, is knowing which questions to ask.
Great. Well, we should wrap up. Thanks all of you for indulging me and coming and chatting with me about this. It's been a lot of fun. And thanks to the audience for watching. We'll put this online so that anybody who missed it can watch again later. Unless there's anything else that anybody wants to add.
Thanks
okay.
For
Yeah, thanks for coming. You can find us all on Twitter, by the way. I'm at AstroKatie. Manda, you're at Manda Yoho. Is that correct? We lost Amanda. We might have lost Amanda. Then Matthew Francis is at Dr. Mr. Francis. And
you always say Dr. Mr. It's just MR.
It looks like Dr. Mr. to me. And of course Robert McNeese, you are at McNeese. So find us on Twitter, and thanks for watching. Bye.